Hi, everyone. My name is Fabio. Thanks to the organizers for having me here. I am a software developer, a Python developer. I work at Recon Digital, which is a London-based company I co-founded a couple of years ago. And you can check out our Twitter accounts, my personal or the company's one there if you want. This talk is about constraint programming, which is a specific programming paradigm that is used to solve a certain class of problems that are known as constraint satisfaction problems. We will see a little bit what constraint programming is about. We will talk about a Python library that allows you to use constraint programming within your Python software, and we will see that in action on a couple of examples. We started using this library, this Python library, to do constraint programming a few months ago, when a client of ours came to us asking for help on a scheduling, on an optimization problem they had on one of their facilities. This client is a large multinational company, and they have a facility where they collect large industrial machinery, large turbines, and they test them. They test those turbines. So in order to test those turbines, they need resources. That is test beds, engines to power the turbines. They need gearboxes to connect the engines to the turbines, and so on and so forth. And of course, in order to create an optimized, a good schedule, a good calendar of all the tests, they needed some software to do that. They used to do that manually, but of course that was far from being optimal. And so we decided to use constraint programming because that problem reminded us of a famous constraint programming problem, which is called the job shop problem. The software that we created is made up of two different parts, the matching part and the scheduling part. The matching part has not really anything to do with constraint programming. It's just a set of basic Python functions. What is needed there is that the kind of tests they run on the machinery that they get. So let me step back a second. I'll describe you a little bit more in detail the process. This client collects this large industrial machinery at their facility, and they have to run tests on those machinery. Those industrial machinery are turbines, are large turbines. Each one of these turbines is only compatible with a subset of the resources available to run the tests. So, for example, suppose that we have 20 test beds, places where those machines have to be placed in order for the test to be run. A turbine is usually only compatible with a few of those test beds, or maybe with a few of the gearboxes that are necessary to connect the turbines to the engines. So the matching part, what it does is that it tells you for every given turbine, which is the subset of resources that are compatible with that turbine. The second part of the software is the scheduling part, and that's where the constraint programming really kicks in. The scheduling part takes as an input the list of jobs, the list of tests that have to be performed, and gives as an output a calendar, sort of a Google Calendar, sort of a scheduling with all the tests and all the starting dates and all the resources that have to be used for every single test. Of course, there is some work under the hood, since you have to be sure that no resource is overbooked. That is, that a gearbox is just used for a specific turbine now and not booked for another turbine. So each resource is just used only once at a time. Just to give a brief mathematical description of what we are doing here. The matching part takes something as an input. Okay, yep, it's there. It's there. So the matching part, for every given turbine T and every given resource R, what it says it tells you how good that resource is to perform the test on the given turbine. And the measure of that, of how good it is just a real number between 0 and 1. So it's a very good match. That resource is a very good match for that turbine if the result is 1, and it's not suitable, it's not compatible if the result is 0, but there can be some kind of fuzzy logic, so the result can be, for example, 0.5 if the resource can be used, but it's not optimal. The scheduling part is a mapping between those sets, and basically what gives is for every turbine T, it gives you back a couple R and D, where R is the resource that you're going to use, that will be used to run the test on that turbine, and the starting date D for the test to be made. Of course, this scheduling function that we just saw have to satisfy a few constraints. First of all, the resource R that is associated with that specific turbine must be compatible with the turbine. So for every turbine, I can only choose a test bed or a gearbox that is fine for that turbine. The test dates that are assigned by the scheduling function must be compatible with the arrival dates. So if I have a turbine that arrives, say, on the 1st of June, I cannot start the test a month before, of course. Also, most importantly, no resources can be overbooked. So as I said, I can only use a test bed one day for one turbine and not at the same time for another one. Also, it's very important, this part, so the optimization part. So the way the scheduling is produced should be optimal or suboptimal. That is, it must be taken into account the time that is taken to run all the tests, the so-called make span. So the total amount of time that is necessary to run the tests on all the turbines that we have. Many of you might have realized that this problem is similar to a very famous problem, which is called the job shop problem. That's a very famous problem in the constraint programming field. One of those problems that you are taught about when you learn the basic principles of constraint programming. The job shop problem says, okay, you have a shop, you have a few jobs with different lengths that have to be run, and you have a few machines within your shop that help you to run the test, to run the jobs. And you have to find an optimal way to organize your jobs within your shop so that the make span, the total amount of time needed, is kept to a minimum. So it's some sort of similar to our problem. Of course, our problem involves many more variables, but the basic idea is very similar. So we decided to investigate what the options were to do constraint programming with Python, and we found a library which is called OR tools. And we decided to use that. We choose that among a few other options. We chose that among a few other options for a few reasons. It's first of all a C++ library, but comes with a Python porting, so it was possible to use that in our Python software without too many troubles. It's actively maintained, which is, of course, is very important too. Is a library created and maintained by a Google team, and they actually use that for part of their work internally, they say. It's actively maintained, and I wrote to them, one of the maintainers, a couple of times. He was very helpful, very responsive, and just a matter of minutes or hours, and he replied. Also, it's actively maintained. It's open source, which for us was a very important point, and it comes with a good documentation. The documentation could be better, but it was good enough for us to understand how it works and to create our software with that. We decided to use constraint programming because our problem falls in the category of constraint satisfaction problems, and so is suitable, well suited to be solved with constraint programming. Generally speaking, constraint satisfaction problems are made up of, are defined by three main parts. The first one is variables. I mean, you have to define what are the variables within your problem. You have to define the domains where those variables live in, and you have to define the constraints that those variables have to satisfy. So, for example, in our case, in the case of our client's problem, the variables could be the starting dates for the tests. The domains could be maybe integer numbers to indicate the dates, and the constraints, all the different constraints that we saw before. I would like to tell you a little bit more about this library and about constraint programming, and I thought of a simple example that is one of the famous examples of constraint programming. There's a reason why there's a background, a chessboard here as a background in this image, and the reason is that this famous problem is called the n-queens problem, and so it involves a chessboard and the queen, the chess piece queen. The problem says that you have, say that we are talking about the 8x8 version. The problem says you have a chessboard, an 8x8 regular chessboard, and you have a set of queens, 8 queens. And you have to place all those queens on the chessboard in such a way that no queen is a threat for another queen. So, for example, you cannot have 2 queens on the same row, because in the game of chess, queens can move horizontally, and so those 2 queens would be a threat for each other. For the same reason, you cannot have 2 queens on the same column, on the same vertical line, or on the same diagonal, because queens can move horizontally, vertically, and on the diagonal. So the problem asks you, is it possible to find a way to place all those 8 queens on the chessboard in such a way that that works, that they are not a threat to each other? The answer is yes, and the answer is more precisely that there are 92 ways of doing that. Of course, you can figure out one way to do that, or even all the 92 ways manually, but it would require a huge amount of time. While doing that with constraint programming, it turns out is very easy. Again, as I said, to define a constraint satisfaction problem, we need to define those 3 pieces: what the variables involved are, what the domains where those variables lived in are, and what are the constraints, are that we want to satisfy. So, for example, in the case of the 8 queens problem, and this part here is called modeling. That is, you have a problem and you find a model that is suitable to be solved with constraint programming. And this part is very important, because depending on how you create your model, you can make a very difficult problem easy to solve, Or the other way around, if you choose the wrong model, you can make a quite easy problem a very computationally very hard one. So for example, in the case of the 8 queens problem, there are at least 2 different approaches. The first approach is the naive one, and it turns out that doesn't work very well. And this approach says, okay, so we have 8 queens, we have our chessboard, we have to figure out how to place those queens. So why not using a different variable for each queen? And of course that variable has to say where the queen is placed on the chessboard. There are 64 different squares on the chessboard, so let's make that variable number 1 is the position of queen number 1, and let's make that variable taking values in the 0 to 63 interval, so that the first variable can take 64 different values. The second can be done for the second queen, the third, and so on. So we end up with 8 different variables, 1 for each queen, that can take values in the interval 0 to 63. Then we have defined our variables, we have defined our domains, we just have to define, mathematically speaking, our constraints, and we are done, in the sense that we have created our model. It turns out that's not a very good model, because the tree of all the possible options, all the possible alternatives in placing all the different pieces would be huge. It would be 64 by 60 times 64 times 64, and so on and so forth. And looking for a solution within that tree would be very time consuming. There's another way of modeling this problem, which is much smarter, and it says, okay, let's keep into consideration 8 variables again, but this time let's take into account that we already know that we cannot have 2 queens on the same row. So instead of saying that the first variable for queen number 1 can take values from 0 to 63, let's just assume that the first variable can take values from 0 to 7, which are the 8 different squares on the first row. Well, it's the same for the second variable, because the second variable is for the second queen that stays on the second row. So that takes values from 0 to 7, and so on and so forth. So instead of having 8 variables with those domains, we have 8 variables with domains 0 to 7. Our search tree, in this case, would be much smaller and and it would be much faster to go over it and to search for a solution. The constraints would be, first of all, we cannot have 2 queens on the same row. But wait a minute, we already said that our variables say where a certain queen stays, and we already know that we have different queens on different rows. So this first constraint is not really needed because of the way we modeled our problem. The second constraint says we cannot have 2 queens on the same column. So the only thing that we have to say is that all those variables, all those 8 variables, will have different values. And then we add a constraint for the diagonals to say that we cannot have 2 queens on the same diagonal. Let's have a look at some code. So, does it work? Yep. I put here a few lines of Python. We are making use of this library, the ORTools library. And we can see what I just said here. That is, in the first part here, we are both defining the variables and the domains at the same time. So what we are creating here is a list of variables called queens, and we are saying that those variables are integer numbers. The domain is the domain of integer numbers between 0 and 7. What we are doing in the next steps, we are applying the constraints. So the first constraint says we cannot have two queens on the same row. But as I just said, this is implicitly satisfied by our model. The second constraint here says that we cannot have two queens on the same column. So we, in the OR tools language, what we say is that the variables within this list, so the queens, must all have different values. In this way, we won't end up with two queens on the same column. And once we have defined this constraint, we simply add it to our solver, which is sort of the core of the OR tools library in this case. Then we have to add other similar constraints for the diagonal part. And once those constraints have been defined, we simply add them to the solver as well. Once that is done, we are basically done. We press a button and we get the solution. To tell the truth, things are a little bit more complicated than this, because the important parts here when solving a constraint satisfaction problem using this library, but generally speaking, are two different parts. The first one is choosing a good model for your problem. The second one, once you have chosen your model, is to define a smart algorithm that allows you to browse, to go through the search of possibilities in a fast, in an efficient, in a smart way. And that's generally, it can be difficult. You have to very well know the problem you are dealing with, and you have to try and take advantage of the specific nature of your problem. So there's not general rule to do that. Luckily, in this very simple example of the n queens problem, but also in our software for our client, the scheduling one, we didn't really have to go into the details of how implementing this algorithm, how doing this search in the tree. So in this second part of the code, which just comes after this, what we are saying to the OR tools library is just, okay, I press a button, you give me all the solutions. And we are just using the default values here in this part. And this is the part where we could tweak the things and ask OR tools to use a specific algorithm to search the tree. But we are using just the default values, and then we sort of press a button, wait for the solution, and it turns out that it's quite fast. In a matter of a few milliseconds, we get all the 92 different solutions. So all the 92 ways of placing queens in the chessboard, on the chessboard, in such a way that we know. I prepared some more code for you. It comes in notebooks file. Those are just basic examples, but maybe if you want to have a look and start from something to do some work, to do something, that could be nice. So I'll show you the links here. So this part here is a Python notebook that you can just check out from this repository here. If you go to GitHub and look for our public repositories on the Recon Digital account, you'll find this one. And within this repository, you'll find very brief documentation that tells you how to start up a virtual environment and what is needed to be, what you need to install to have this thing working. And then there is a little bit of code, very easy stuff, nothing serious, And so again, this is just the code that you have seen before. We have this part here where we define the variables, then the constraints, and then the actual work that is done by the OR tools library. And at the very bottom, we have printed out, displayed the solutions, the 92 blocks that represents a sort of a poor man, poor person chessboard. Here, just using Unicode charts, with the position of the black squares here, which should be the queens. And so you have all the different solutions. We should have another example, which is closer to the initial problem that I described, so closer to our real software. And it's called the job shop problem example. So again, the same repository, you go there, you find this. This is, again, just basic code, nothing fancy. But at the same time, I can tell you that it's the most important part of the software that we created for this client of ours is there. So the rest, other than that, is just some Python, some wrapping, some minor stuff. The most important things are there. So the first part here, we just define a few classes and functions and the initial setup for our program, for our notebook. Then we create the variables again. And I'll tell you a little bit more about this in a minute. We define our constraints, and then at the very end, we press the button. So we start the so-called solving stage. And what we have here at the end is, again, the poor version of a calendar where we have all our jobs within the shop. The different lines are different machines where the jobs are supposed to be performed, and the different blocks, the colored blocks, are the jobs that we want to perform on machine 00, machine 01, machine 02, and so on and so forth. And on the x-axis, what you have are days, dates. So we start from date 0, for example, here, testing this, running this job on machine number 11, and testing this job on machine number 14, and so on and so forth. On day 2, we start with this job, and so on and so forth. And the reason why those jobs were organized in that way depends on the arrival date of the job in our shop. So when we can actually start running that job, depends on the kind of resources that that job relies on to be tested, to be run. Vladimir, how about timing? Okay, so I'll tell you a little bit more about this part here. Okay. So, what we are doing here is we have jobs, and each job is a class that has a length, of course an ID, an identification code just to keep track of that, has a set of resources that are compatible with that job. So in our shop, in this case, we have a set of 20, 0 to 19 different machines, different resources that can be used to run our jobs. Each job is compatible with a subset of those 20 different machines. So for example, this job here was probably compatible with, of course, with the first resource and maybe a few others. All this data is created randomly at the start. You can have a look at the code. And we assume that each job is only compatible with a subset, I guess, of 3 resources. There should be a parameter at the very beginning to set that. So here we are saying number of compatible resources per job is set to 2. So yeah, you can, of course, you can change that. You can play with that and change all the values. How can we define, how can we model our job shop problem like we did, as we did with the n queens problem? There's a nice trick here that, of course, is nothing we invented, but we just saw other examples about that. And the trick is, let's create a dictionary, let's create a grid that has on the, say, on the x-axis, all the different resources that are available, and on the y-axis, all the different jobs that have to be performed. Then each different element within this grid will be basically will correspond to a map of a job and the resource. For each one of those elements, so for each element within that grid, we create a so-called interval var variable. The interval variable is a variable that is provided by the OR tools library, and basically it is a variable that has a starting date, an ending date, and a switch that says, okay, this variable is actually going to be performed, and this other variable is not. So it's a switch, am I going to be performed or not? In this way, we have for each job a set of different variables, each one for each different resource. And we are going to set a constraint just over here that says that each job has to be performed only once, so that among all those variables that are associated to that job, only one will have that switch to be performed, switched on, and all the other variables there will be just turned off. So if we do that and add the other constraints, so for example, this constraint is the one that I just mentioned, each job has to be performed exactly once. Then the second one, each resource can only be used by one job at the time. And we do this using this bit here, this function that is provided by the OR tools library, disjunctive constraint. So that's basically says whatever you put here, and this is a list of different variables, whatever you put here, that is going to be performed not at the same time. So in a sort of disjunctive way. Then we have the solving stage, and again, we were lucky enough, we didn't have to tweak our software in a specific way or to provide any smart algorithm to look for solutions to the problem. So what we are doing here is just telling the OR tools library, okay, go, start, and give us back the solutions, and we are limiting the number of the solutions that we get with this constant here. It should be 10 or 20, and all the solutions that we get are listed here. I hope this kind of poor diagram is clear enough. So again, we have resources, each one on a different line. We have time on the x-axis, so these are days basically, and the colored one are the jobs that we are performing, that we are running. And as you can see, not all the solutions are equals. There are a few of them that have a make span which is longer, and others that have a shorter make span. And again, the make span is the total amount of time that takes to run all the tests from the start of point of the very first one to the ending point of the last one. A way to optimize your results would be to add a couple of lines of code here, and for each result that you get back from the OR-tools library, to measure how good that result is. And of course, the definition of good depends on your parameters. For example, it could be it is better if the make span is shorter, and then you can organize, you can filter your solutions depending on that result. So that this part is over. We should have another slide here. So again, constraint programming, it can be very useful if your problem, the problem you are trying to solve, can be modeled as a constraint satisfaction problem. There are good libraries to do that in Python. One of that is the OR-tools library. There are two very important parts involved here. The first one is creating a good model for your problem, because otherwise simple problems can get very hard. And the second very important part, is choosing a smart algorithm to look for a solution. This is what we did for our client. They are happy with the software, and that solved their problem. So I think I'm done. Thank you very much. And yeah, hope that was interesting for you. Thanks.
Thanks, Fabio. Any questions? Yeah. Oh, okay. I think the girl will be first.
Hello, my name is Julia. I have a question. Have you investigated, or maybe you know, what is under the hood of this library? Which algorithms? Yeah. So maybe a genetic algorithm, or maybe simplex method? You should know.
It shouldn't be a genetic algorithm. I didn't really investigate the code, but what I think they are doing under the hood is just looking for a solution within a tree. So with the usual different algorithms, depth first, breadth first, and backtracking, and all those basic algorithms of artificial intelligence. You can choose different ones depending on your requirements, again, depending on the nature of your problem. But I don't think that genetic algorithms are used in this specific case. There could be a part of the OR-tools library where that provides you that functionality to do genetic algorithm stuff, but I'm not sure about that. You should check that out. Yeah. Yeah, thanks.
Thanks for presentation. My name is Ivan, and I have a following question. How you came up to use some library? Because I'm not really into constraint programming, but if I would have such a problem, I think I would try to solve it by pure Python, because you know, like for my practice, when you use some library, you always get in the situation when the library doesn't fit your specific condition.
I think you're right. I think it's always a matter of trade-off, because on the one side, what you're saying is perfectly true. It's a one more dependency to take care of. At some point, the software could be not maintained anymore, and or for there are several different reasons why I agree with you. But at the same time, it's bad reinventing the wheel. And since the amount of code that's there's already been done by these people is I think quite a lot of code. I guess in this very case for us, using the OR tools library, or possibly another Python library that already does that, was the fastest option. Yeah. Also, our problem, as I said, we were lucky enough, didn't really require us to write any kind of weird algorithm, very advanced stuff. So it was, as you can see, what we have done is just a few lines of Python code. Of course, there's much other stuff around that, but so that was very fast for us. That helped us a lot in terms of speed. Yeah, that's the reason. Yeah.
Thank you very much for talk. My name is Nikolai, and well, first a short comment for the previous question. I've briefly looked at this library or tools, and as far as I see, it, for example, contain a GLPK solver, and I had some experience with this, and it is really huge piece of code.
Okay.
Really huge and really complex. And and I have asked a question. Have you did you do only integer optimization? I mean days or hours and tools, not the floating point math, not the floating point problems.
No, that wasn't required. I mean, what we wanted to optimize was the delay between the starting date for each test and the arrival date of the machine to be tested, and keep that delay as little as possible. That's the optimization that we were looking for. We are currently, to tell the truth, to be honest, we are currently implementing another kind of optimization, because as I said, not all the resources are equally good for a certain turbine, for a certain machine. So there are different certain for example, gearboxes allow you to it can be used for a machine, but they are really consuming in terms of energy. So we are trying to optimize that part, the energy part, how much energy the facility spends in order for those tests to be performed. Yeah.
And another question. You mentioned that you tried several libraries.
Yeah.
Have you some kind of list of these, maybe with short summaries, maybe on your GitHub?
I haven't prepared that, but I can do that. And yeah, there are several other options. I guess, if I remember well, less than a dozen, but around 10 different libraries. Also, depending on your problem, you might find very specific libraries that maybe weren't good for our problem, but could be very good, very specific for yours. So, yeah, maybe we can stay in touch, and I'd be
surely
happy. Yeah.
Thank you. Thank you again for your talk.
Thanks. Thank you.
Okay, and a question from me. It's a quite common question in the Python world. What about the performance?
Yeah, they are very good. That was, of course, a scary part for us, because when we started this project, we were given some specifications by the client, but we really didn't know how fast could be on Python, but generally speaking on a computer, to manage a few hundreds jobs with several dozens different resources and dependencies and things like that on a machine. and it turns out that it's feasible. And in order to build the scheduling, so to run that algorithm basically with a few other constraints and complications, it takes just a few minutes. So the performances are good enough for us. We have just a Celery script. The scheduling is launched with the Celery script every few hours, and yeah, that's done.
Okay, thank you. Yeah.
Hello, my name is Dmitry. I'd like to return to the previous question. Have you tried to compare implementation in Python and plain C++?
No,
So we can.
Yeah.
I'd like to know, can we compare or measure the difference in time that can give us Python?
Yeah.
compared
So
to C++?
the answer is no. We didn't make the comparison. But what I can say is that under the hood, the library is of course a C++ library. There's only a wrapper around that allows you to use that with Python. So I am sure there can be differences, but probably there are not going to be huge differences since the underlying code is still C++. And again, since we were lucky enough that that's working fine, we were lazy enough not to think of any other kind of optimizations because that was good enough. Yeah.
Yeah. Another question from me. Okay, you solved the problem of the 8 queens.
Yep.
Did you try to solve the problem of playing chess?
No. We are trying with Go. Maybe.
Yeah, maybe playing Go.
Just
then.
kidding. Just kidding.
Okay. Okay, I think that's all. That's all? Yeah, that's all. Thanks to you.
Thank you
Thanks
very
to
much
you
for
all. So
listening.
you can